So today we're going to continue our discussion talking about organic molecules, and today we're going to continue by starting by talking about organic molecules, the alkanes. So the molecules that we're talking about being organic compounds, these are hydrocarbons, which means they only contain carbon and hydrogen. So they don't have anything else besides hydrogen and carbon. And of the hydrocarbons that exist, there's a few different types, one of which are alkanes. Alkanes are hydrocarbons that are saturated, which means that they're full of hydrogen. They don't have any double bonds. They don't have any triple bonds. All of the bonds in an alkane are single bonds, and those are all carbon-hydrogen or carbon-carbon single bonds. So if you are a saturated hydrocarbon, that's all you have. If you're an unsaturated hydrocarbon, you can only contain carbon and hydrogen, but you may contain double bonds as well. So you may also contain carbon-carbon double bonds or even carbon-carbon triple bonds. And a molecule that has a double bond is referred to as an alkene with an ENE, and then a molecule with a carbon-carbon triple bond is an alkyne, a YNE. So depending on what kind of hydrocarbon you have, you may have single bonds, double bonds, or triple bonds between those carbons. So this is some examples of some hydrocarbons. So you can see here all single bonds to the alkane on the far left over here versus the alkene has a double bond between two carbons and the alkyne has a triple bond. And if you were to kind of look in larger molecules, it may be that there's only one double bond in your alkene. So if you look at the center alkene right here, there's lots of other single bonds present between the hydrogens and the carbon, and even between some of the carbon atoms, there's some single bonds like the CC single bond right here. And that's okay, that's still an alkene because it still does contain one double bond. As long as you have at least one double bond, you are an alkene. Versus if you have all single bonds, then you're an alkane. So you can see on this molecule here, this saturated molecule, all of the bonds are single bonds, and that makes this an alkane versus an alkene or an alkyne, which have a triple bond somewhere. So triple bond somewhere in the molecule will make this an alkyne. Single bond anywhere, everywhere would be an alkane. And if there's a double bond anywhere, it becomes an alkene. The aromatics are similar to the alkenes. They have double bonds, but they also have those double bonds arranged with the carbons in a ring. So a double bonded carbon making a ring is what's called an aromatic. It's a special type of alkene where it has double bonds, but those double bonds put the carbons into a loop which closes on itself. So that's a special type of molecule, and it's referred to as aromatic because there's extra chemistries involved in those molecules. But those are all what we would call unsaturated. Unsaturated molecules contain either double or triple bonds. So alkenes and alkynes and aromatics are all unsaturated molecules. Versus if you have only single bonds, then you're a saturated molecule like an alkane. So alkanes are the only type of saturated hydrocarbon. Every other hydrocarbon is unsaturated. So to talk a little bit more about the properties of alkanes, alkanes are saturated. That means they have only single bonds, and they're hydrocarbons, which means they only have carbon and hydrogen. So something like a CH4 or a CH3 bonded to another CH3. Those would be two examples of some hydrocarbons that are saturated. All single bonds, all contain carbon and hydrogen only. And if you look at all the different versions of hydrocarbons and you start looking at all the saturated hydrocarbons, you'll start to notice there's a general formula. You'll see stuff like CH4, C2H6, C3H8, C4H10. And basically, it's number of carbons and the number of hydrogens in that atom is just twice as many hydrogens as there are carbons plus two more. So if you look at the carbon right here, there's one carbon, twice as many carbons as two, and then plus 2 is 4, and there are 4 hydrogens for that carbon. Or over here, there's 2 carbons, twice as many carbons would be 6, and then 2 more would be 8, and it turns out this atom has 8 hydrogens. And you could do that for all the different alkanes that exist, and all the alkanes have this general formula, CN H2N plus 2, or there's twice as many plus 2 hydrogens as there are carbons in an alkane. And hydrogens and alkanes can take on all sorts of different shapes. You can see here what's called a linear molecule of C4H10, and that's just 4 carbons in a row, just like over here, 4 carbons in a row. And that would be called the linear molecule or a linear hydrocarbon because all those carbons go in a line. The first carbon's connected to the second carbon's connected to the third carbon's connected to the fourth carbon to the 5th, to the 6th, to the 7th. It just goes down a straight line, no branching. Versus this hydrocarbon over here has a branch. It starts off by going this way, but then at some point it branches and it also goes this way. So a branched hydrocarbon may be more like this molecule right here, where there's two chains of carbon going along the back and then another one that branches off onto the side right there. And that would be called a branched hydrocarbon conformation. And because of that, you can get all sorts of different structures of hydrocarbon alkanes. So this is why there's billions and trillions of different hydrocarbon conformations molecules, because with the same C4H10, I can draw two different structures. I can draw one that's a straight line like this one here, or I can draw one that's a straight line with a T coming off of it like here. So this is two different conformations of the same molecule. They have the same formula. If you were to count, they both have 4 carbons, and they both have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And over here, 2, 4, 6, 8, 10 hydrogens. So both of these have 10 hydrogens and 4 carbons, but the structure of one is very different than the structure of the other one. And those are called isomers or structural isomers, where same formula but different shape is being produced. So alkanes have a lot of different conformations that they can be in, because in addition to changing how they're arranged, they can also be kind of rotating around. These molecules are in lots of motion, they're moving around. And if you think about this molecule, I can turn this molecule around any one of these bonds. So I could take this bond right here and I could twist it around like a propeller, and I would just move these hydrogens around in a space. But I could also twist around this molecule right here, and rather than having this part pointed up, I could twist it so it's pointed down, but it's the same molecule. All I did was twist it, so rather than having it in this kind of U shape, it went to this more kind of NW shape. So going from a U shape to more of a lightning bolt shape is just by twisting one molecule, but I didn't change the molecule in any way. All I did was kind of rotate around this bond right here. So it's kind of like a twisting action, but it doesn't change the molecule. Those carbons still go 1, 2, 3, 4, just like over here they go 1, 2, 3, 4. So I haven't changed any of the orientations, the carbon connections, right? 1 carbon, 2 carbon, 3 carbon, 4 carbon in that same pattern. It's just now that I've twisted that pattern around, it has an up versus a down, because I'm allowed to rotate around any of these carbon-carbon single bonds. Carbon-carbon single bonds can twist and rotate like the axle of a wheel or like a propeller, and that means you can spin these molecules around, but you don't change the molecule. It's still the same, versus other molecules where you may have different structures from actually moving those carbons around. So you can kind of see here, some of these molecules are actually just the same molecule drawn slightly differently because I twisted it. Like if I took this long carbon chain right here and I kind of bent it so that this one was pointed up instead of pointed to the left, and then I bent this one over here so it was pointed down, then I would go to this structure right here where I have this kind of M shape now. But all I did was just take that carbon and kind of bend it. I didn't change any of the orientations. I didn't change any of the connections. It still has carbon 1 right here in red connected to carbon 2 in green, connected to carbon number 3 in blue, connected to number 4 in purple. And then the last one we'll leave blank. So you can see I still have the same connection. Still goes 1, 2, 3, 4. I didn't change that structure. And the same thing here for this one. It goes 1, and then the green one is connected to it, and then the blue one is connected to it, and then the purple one's, oops, that's purple, and then the blue one's connected to it here. It's still that same pattern. They're all connected. All I did is just kind of twist and bend. And you could almost think about if you were to grab this one from here and you were to pull, you could kind of straighten it back out to form this structure again. Or if you kind of crunched up and pushed this one down over here, you would get it to form and look like that one there. So those 3 molecules on this side right here are all the same structure. They all have the same structure, they all have the same connectivity, they're just been rearranged a little bit. Versus if I go to the ones on this side over here and I try to do that same trick, and I say, all right, I'm going to start here, this is the first carbon, it's in green, or red, and the red one is connected to a green, and the green one is connected to a blue, and the blue one is connected to purple, but purple was connected to this one here, let's put a black line on all three of them. Purple is supposed to be connected to a black line. The black line one, though, is down here. It's not over here. It's not connected to purple. So you can see here, this molecule is a different structure than the ones over here. And we could do the same thing for this one over here in the center, and we would see the same thing where it has a red molecule connected to a green, connected to a blue, connected to purple, and then the black one on the left is connected to purple, but down here it's connected to the blue. So these two on this side are also the same molecule, but they're not the same molecule as the ones that we circled in the yellow on this side here. So there's actually two different types of molecules drawn in this structure. One has one structure where they're all in a line, and one has the structure where there's a branch. So these are two different isomers of the same molecule formula, but they have different structures. So one has 5 carbons all in a linear pattern, and one has 4 carbons in a line with a branch coming off of them. So those are two different conformations of the same alkane molecule. They both have the same formula, C5H12. You could count 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 3, 6, 9, 12 carbon hydrogens here, 3, 6, 10, 12 carbons here. So they both have the same number of carbons, they both have the same number of hydrogens, but they do have slightly different shapes because this one has this branch with a breaking point coming off of it versus the other one has a long branch with no chain branches off of it. So two different structures of the same formula, and that results in organic molecules having tons and tons and tons of different structures because you could rearrange those. So alkanes do have some general properties though. So alkanes have some general properties that generally, as they get longer, they get to be longer and longer molecules. As you add more and more carbons onto them, they become more likely to be a solid. So small alkanes with 1, 2, 3, 4 carbons, those are generally gases, and that's these first molecules here. And then as you get to slightly longer carbon chains, you get to more of a liquid state. And then when you get to really long states, you get to a carbon that's a solid. And you can kind of think about that like a plate of macaroni. So if you have like a plate of macaroni and you have all the macaroni molecules there, those molecules are kind of easy to move around. Those are your small chain hydrocarbons. Those have 1, 2, 3, maybe 4 carbon molecules on them. And those ones, those low macaroni molecules, aren't held together very well. And you can kind of grab one off no problem. And if you dropped your plate, they would make a big mess because those molecules aren't very long. They're not held together very well. Versus long chain molecules like the 21 and longer that are a very big solid, those are more like a plate of spaghetti. And spaghetti is very long and it kind of weaves and gets stuck with all the other molecules. So just like with the spaghetti molecules here, if you kind of grab it, you can kind of get a lot of the other molecules to come along for the ride. You can get a lot of the spaghetti onto one fork. You twirl it, you can pull up a whole big pile. And that's because that's a really long molecule and it's able to bend and move around. And when it does that, it grabs all the other molecules with it. And there's a lot of forces between those spaghetti molecules, and that means you can grab a lot at once. And the same thing is happening in our solids here. Those really, really long chain carbons with 20 or longer carbons on them are weaving around and they're getting tangled up in each other, and that lets those molecules hang on and hold each other together, and that keeps the molecule as a solid by having a lot of force between them. Versus the gas molecules are very small, they're not very big, they don't get interwoven as much, and they don't hold together very well, and you only have to add a little bit of energy to get them to convert to a gas. So those are some of the properties of alkanes, how they get, as they get longer and longer, they get more likely to be a solid and more likely a wax. Other properties they have is that they're not very soluble in water. These only contain carbons and hydrogens, so C's and H's. That's a very nonpolar molecule. That water is a polar molecule, so water is going to dissolve polar molecules. Water is not going to like having nonpolar molecules in it, so alkanes don't dissolve in water very well at all. And they tend to float. They're also very low density. So because they're less dense than water, they're going to float. They're not going to interact with the water. They're going to stay outside the water, and they're going to float on top of the water. So those are some properties of alkanes in organic compounds. And they're also, of all the organics, the least reactive. So these molecules don't do very many chemical reactions. They're very relatively inert. So those are some properties that alkanes have. compared to other organic compounds. Alkanes have a naming convention too that you can kind of understand. You can always identify an alkane because they end in ane. So hexane or butane or methane, they all end in ane, and that's a way of letting you know that those are alkanes. The methyl, F, prop, all those parts of the prefix of the alkane also tell you how many carbons it is. So an octane would have 8 carbons in it. So oct means that there's 8 carbons, ane means it's an alkane. Pentane means that it's a 5-carbon alkane. Decane would be a 10-carbon alkane. So by just looking at the name of the alkane, you can figure out how many carbons are attached to it and whether it's an alkane or some other molecule. The end of the molecule name tells you what kind of functional group it has, if it's an alkane or an alkene or an alcohol. And the first part of the name tells you how many carbons there are in it. So if we wanted to name some alkanes, we could just look how long the longest carbon chain is. So for instance, this molecule here is a pentane because it has a chain that's 1, 2, 3, 4, 5 carbons long. So you look for the longest chain. There's a short chain as well that goes 1, 2, 3, but that's be the shorter chain. We would identify the longest chain we can, and the longest chain we can find is this one that has 5 carbons. This one also has a 5-carbon chain, 1, 2, 3, 4, 5 here is a long 5-carbon chain. There's also a 2-carbon chain down here and a 3-carbon chain over here, but we're going to use the longest chain that we have to name it. So the longest chain we can see is a 5-carbon chain. Down here, we have a 3-carbon chain. We have a 4-carbon chain. We have a 4, 5, 6-carbon chain, but we also have a 7-carbon chain. So because we have a 7-carbon chain, that's the longest chain we have, that means that this is a heptane molecule. So you can name alkanes based on the longest chain that you see, and that's just looking through and drawing and trying to find the longest number of carbons that you can get in a single count without having to lift your pencil. And then when you do that, that's the number we're going to use as the prefix. And then because these are just alkanes and they have no other functional groups, we'll end it in ane. So this is a heptane type molecule here, number 7, 7 carbons attached to a single chain. And then there's also just some little branches coming off of it, but that's okay. We don't need to worry about the branches. So these 3 branches right here, we can just ignore, and we can just see this as a molecule that's got a single branch, so single long chain of 7 carbons long. That means that this parent molecule is a heptane type molecule. Alkanes also can exist in a circle though. So just like you can have like 5 carbons here in a long line, you could take that same line of 5 carbons and you could connect them back to the start. And that's what would be called a cycloalkane. So alkanes that are in a ring are cycloalkanes. So this would be cyclohexane right here with 5 carbons all attached in a ring versus a regular pentane would be just 5 carbons attached in a line. You can do that for 4 compounds too. You have butane right here with 4 carbons, and butane with 4 carbons in a circle, which becomes a square, is a cyclobutane. So these are all single bonded carbons. They're going to generally have the formula C2H2N. So if you count the hydrocarbons and the cyclocarbons right here, the cyclocarbon right here, 1, 2, 3 carbons and 6 hydrogens. 5 carbons over here and 10 hydrogens. So they're going to have twice as many hydrogens as they do carbons, and they're only going to have single bonds. So if you have a single bonded compound with twice as many hydrogens as it does carbons, that's an indication you have what's called a cycloalkane. It's the same as a regular alkane, but they're linked back onto itself in the end, so it forms a circular compound. So you can name cycloalkanes, and you name them very similar to the way you would name a regular alkane, except rather than calling this propane, this is cyclopropane. So it's got 3 carbons, which would be propane, but it's 3 carbons in a circle, it's cyclopropane. 5 carbons in a line is pentane, 5 carbons in a circle is cyclopentane. So the cyclo is just telling you that this is a cycloalkane or a circular alkane. Butane has 4 carbons, cyclobutane has 4 carbons in a ring. Hexane is 6 carbons. Cyclohexane is 6 carbons in a ring. Decane would be 10 carbons. A ring of 10 carbons would be cyclodecane. So those are just some of the other techniques for naming those, but they all end in ane. Ane, that means that they're all alkanes. So they'll always end in an ane if there's no other functional group present there. So that's just one of the techniques for naming. So that's one of the things we've learned about today. So we've learned about alkanes, and we'll fill this chart in with the other types of names as we learn other organic molecules and the techniques for naming them. But right now, if you see a molecule whose name ends in ane, that's a sign that you're an alkane, and that means you have no double bonds or no triple bonds or any other group attached to your hydrocarbon. But we also have other functional groups like the alkenes and the alkynes, which are also hydrocarbons with either double or triple bonds. So those are what are called the unsaturated hydrocarbons. So alkenes and alkynes are unsaturated, and those are other types of hydrocarbons that we may see if we do have a double or even a triple bond present in our molecule. So when we're looking at hydrocarbons, again, we're only looking at molecules that contain carbon and hydrogen, nothing else. So no oxygen, no nitrogen, only carbon, only hydrogen. And it may only be single bonds like the alkanes, or it may have double or even triple bonds like the alkenes and the alkynes. So we're going to talk a little bit more about the hydrocarbons, but now we're going to talk about hydrocarbons that have double or even triple bonds. You can see examples here again. So this is a triple bonded carbon-carbon triple bond, which means that this is an alkyne. Over here, you can see a carbon-carbon double bond. That makes this an alkene. And not every carbon has to have a double bond. You can see here one of the carbons has a triple bond, and one of the carbons just has a single bond. You can see here one of the carbons has a double bond, and the other carbon has a single bond. But as long as there's just one alkane double bond or one alkyne triple bond, the molecule is an alkene or an alkyne. You only need one double bond to become an alkene. If you have no double bonds at all, that's the only way you can be an alkane. So the only way to be an alkane is to have no double or no triple bonds at all. As soon as you get a double bond, you become an alkene. As soon as you get a triple bond, you become an alkyne. So alkenes are the first class of unsaturated hydrocarbons. And here's some examples. You can see all of these have in common, they all have a double bond somewhere. So this one has a double bond, this one has a double bond, this one down here has a double bond, here's another double bond, and the double bond is in different places in some of these molecules. So simplest alkene is just C2H4, double bond between the two carbons, and then you get more double bonds later. So C3H6, double bond between those carbons. Down here, C4H8, double bond can either be on the end, or it can be in the middle, or it can be somewhere else entirely different. So you have a general formula for your alkenes of C2, CH2N. So twice as many hydrogens as you have carbons, but you also have a double bond. So cycloalkanes and alkenes both have that same general formula, C and then H is twice as many Cs, but you're going to have a double bond in your alkene versus your cycloalkane will not have any double bonds. So if you see two chemicals with the same formula, C2 or C6H12, it could be an alkene, it could be cycloalkane. You have to see, are there any double bonds present? If there's a double bond, then you know it's an alkene. If they're all single bonds, you know it's a cycloalkane. And just like with the alkanes, you can move these around. You can either have a nice linear compound like these two right here, where these are linear molecules, no branches, or you can have branches. And the double bond can either be on the main chain or it can be down on the branch. So here you can see an alkane which has a branch group and it has the double bond there. Double branch could have been somewhere else, or it could be on the main carbon. And these are all structural isomers of C4H8. These all have 4 carbons, these all have 8 hydrogens, but the double bond is in different places in those different molecules, and therefore they do have different structures and different properties. Now remember, when we're talking about hydrocarbons, the carbon can be in a couple different geometries. Carbon, when it has a single bond, has a different geometry than carbon when it's a double bond. If you think about taking 4 balloons and balancing them on top of each other, you'd have 3 balloons on the bottom and 1 balloon kind of balanced above. That's kind of the shape of a tetrahedral or a carbon with 4 things attached to it. Versus if you only have 3 things, you can make a nice flat plane. That's the chemistry of a carbon with a double bond and only 3 things attached to it. You can see here an example to show that these are three-dimensional objects. The carbon in the alkenes with the double bond, though, is going to be a flat molecule with a double bond forming one of the lines of that flat triangle, versus the alkane with the single bonds everywhere is going to be more of that tetrahedral pyramid type shape. So depending on what kind of molecule you're working with, whether or not you have single bonded carbon or double bonded carbon, you're going to get slightly different structures and slightly different shapes. The alkenes with the double bond are going to be very flat molecule, very planar molecule, versus the carbons in the tetrahedral CH4 alkanes are going to be much more three-dimensional carbon molecules. And because of that, when you think about this, remember that that double bond also is going to keep things from rotating. So just like in your wrist, you can kind of twist your hand around a little bit, but if you grab your wrist, you can't rotate your hand anymore. You can kind of twist your hand around, but then when you grab your hand, it doesn't move. That's the same thing over here with these alkanes. So when you have an alkane, you can do a twist around. It's like a little propeller. You can hold this carbon side, and then you can twist this molecule all the way around as much as you want, and you could have either the fluorine pointed up, or you could have the fluorine pointed out, or the fluorine pointed down. That's the same molecule, though it's just rotating around. With an alkene, that second bond there is holding twice as much, and now we can't rotate around on this side anymore, because we can't rotate this molecule because that double bond is holding it too tightly. Just like if you were to hold your wrist and then try to, or hold your arm a little bit above your wrist and then try to rotate your hand, you can't do it because you're holding all those bones in place and it doesn't twist around freely anymore. So in alkenes, free rotation isn't possible. And also in alkenes, these molecules are very flat and planar. So you can see an example here, or when we draw on it, you can see how this molecule is a flat molecule. It's like holding a plate. Alkenes are planar molecules that are very flat. Alkanes are very three-dimensionally shaped molecules because these have that tetrahedral geometry. These have that planar, trigonal planar geometry. So alkenes are flat molecules, kind of like a piece of paper, where all the carbons and hydrogens are all on the same plane, versus an alkane has this kind of three-dimensional structure to it. And you can see here examples of, again, remember, we can rotate around the bonds in an alkane, but we can't rotate around the double bonds in an alkene. And because of that, we'll get different structures with the carbons maybe pointed upward or downward because we can't rotate around that molecule to generate a new structure. It means we're going to have new types of alkene isomer molecules where we have the same formula, but two different structures, and the molecules may look relatively similar. So when we look at the alkenes, there's a lot of different molecule orientations that we can have. And because we can't move the double bond and we can't twist about the double bond, we may get different structures. So you can see here 3 different types of alkenes that all have the formula C4H8. Here it's forming, again, a U-type shape where it goes down and back up. And we can't rotate around this bond right here. So because we can't rotate around that bond, this structure here is going to be different than the one here where it's more of the lightning bolt type shape, because again, I can't rotate around that bond, so it's locked in that downward facing position here, and it's locked into that upward facing position right here. So these are 2 different molecules where one is pointed down and one is pointed up because I can't rotate around the double bond because the double bond is held in place. Same thing here with the methylpropane molecule here. There's a double bond here, and that's a different shape than the ones over here because of the orientation of the molecules. If we were to kind of assign colors to all these molecules, the first one we'll say is purple, so we'll make the first one purple. The second molecule will make green, green, and green, and then attached to the green is a carbon with a double bond, so green is connected to red with a double bond, but over on this side, the last carbon is attached to red. Over here, the last carbon is attached to red. Over here, the carbon isn't attached to red, it's attached to green. So this is another structural isomer here. So this is a structural isomer of the two molecules. And then these two are geometric isomers of each other because they're the same orientation, the same connections. It's just one is pointed down and one is pointed upward. And that's sometimes called cis-trans isomers because if you look, it goes purple, green, red, yellow, purple, green, red, yellow, but one is pointed up, the yellow is pointed up on the left, and the yellow is pointed down on the right. So that's what's called a geometric isomer of the C4H8 molecule. So you can get all sorts of different shapes in these alkenes, and that's going to cause these molecules to behave differently as drugs. It's going to cause these molecules to behave differently as other kind of chemicals when you start reacting them with different molecules, and it lets them serve as signals and hormones. It lets them do all sorts of different structural jobs by having these different structures that they adapt from the same formula. So hydrocarbons can be named. We already talked about how we can name an alkane, and that's just using an ane ending. So if you see any molecule and you see it end in ane, then you know you have an alkane, and that means you're all single bonded. Versus if you see a molecule with an ene ending, then you know it's a molecule with a double bond. So just by looking at the last few letters of an organic chemical's name, you can figure out, does it have single bonds? Does it have double bonds? What kind of groups are attached to it? So alkenes have this convention where we name them and their names end in ene. So you can see some examples of some alkenes here. We know they're alkenes because they have double bonds. There's a double bond here, there's a double bond here, there's a double bond here. And because of that, these all end in ene. So that means these are all alkenes. And then just like with the alkanes, we name them based on the longest chain that they have. So this one goes 1, 2, there's a short chain that has only 3, and there's a longer chain that goes 1, 2, 3, 4, 5. So because the longest chain is 5, we would name this for 5 carbons. 5 carbons is a pentane molecule. If it was 5 carbons with a single molecule, it would be pentane. This is pentene though, because it has a double bond. Same thing down here. This longest chain that we can find, there's one with 3, there's one with 4, there's one with 7, there's one with 6. 7 is the longest continuous chain of carbons that we can make, which means that this is a hept molecule. Hept means that you have 7 carbons, and because this is 7 carbons with a double bond, it's heptene molecule. You can also have alkanes that have a ring, so you can have cycloalkenes. So this would be a cycloalkane, no double bond, versus a cycloalkene with a double bond. So you can name double bonded ring compounds as well as a cyclohexene, because this is a 6-carbon chain, but it has a double bond and it's in a circle. So we can tell it's in a loop because it has the word cyclo around it. We can tell it has 6 carbons because it has the word hex in it. And we can tell it has a single double bond or a double bond because it has an ene ending. If it had a single bond only, it would be an ane. The other thing though, when we're naming our alkenes, is that if there's 2 molecules and there's a branch somewhere where the chain can either follow the double bond and stay on one side or go to another side, then we may need to also indicate which way the chain went. So on that's this idea of cis and trans molecules. So a cis alkene has both of the carbons on the same side of the double bond. And you can see here, if we draw a line through the double bond, both of the carbons are on the same side of the double bonds. And it's kind of shaped like a sideways C. A C is looked like this. And if you were to draw a loop through the carbons, you would go down and back up, and you'd be drawing a kind of C shape. So you have a cis butene molecule. This is butene because it's got 4 carbons. It's an ene because it is 4 carbons with a double bond, but this is cis butene because it has both of those carbons on the same side of the double bond. Versus over here, a transbutene starts here, goes down, goes through the double bond, and then ends up on the other side of the molecule. So just like a transatlantic flight flies across the Atlantic Ocean, a transbutene molecule goes across the double bond. So a trans molecule, like a butene here, this is still butene because it's got 4 carbons, still has a double bond, which means it's an ene, still has 4 carbons, which means it's a butene. And because those carbons are on different sides of the double bond, this is transbutene. This molecule here, though, also has 4 carbons. 1, 2, 3, 4. But when we name molecules, we name based on the longest chain that's there. And if we were to count the chain, it goes 1, 2, 3. So this is only 3 carbons in a chain, which means that it's a propene molecule. Pro is 3, ene means that it has a double bond in it. So this is just a propene molecule. It's not a butene molecule, and it's neither cis or trans because there's no chain. The chain stops here. The chain doesn't go across the double bond the same way that the chain goes across the double bond here. So you can see here the chain started up here, goes to the double bond, and then it continues down. Here the chain starts up here, it goes to the double bond, and then it stops. So this one doesn't have a cis or a trans name system. This is just to show how we can kind of do that again if we were to look at the molecules kind of with a little bit more shading like I did a second ago. And you can see if you look at all the carbons, you can see all the carbons are on the same side of the double bond. On this one, it makes a C kind of shape or a cis molecule. Versus here, it goes across the double bond, which makes the molecule trans. And then this one isn't cis or trans because the carbons actually stop. There's no more carbons after the double bond. They're both hydrogens. So it starts up here, goes to the double bond, goes to the carbon, and then it doesn't go anywhere else. And that means that this isn't a cis molecule or a trans molecule. It's just a propene molecule. So those are some of the ways you can name alkenes. You may need to use cis or trans. You may or may not, depends on how large the molecule is, but always look and find the longest chain that has a double bond in it. We're going to name it based on that length of that chain. So since these two on the left had 4 carbons, they're butenes. Since the one on the right only had 3, it's a propene. And then maybe you would use cis or trans if that chain continues from one side of the double bond to the other side. And then you would use cis if they're on the same side of the double bond, and trans if they're on opposite sides of the double bond. Here's just some more examples where you can see, again, how molecules are either cis or trans. You have to have 2 different groups attached to a carbon on both sides to be cis or trans. So if you look here, right, this is one group on top and a different group on the bottom. Same thing down here, one group on the bottom, different group on top. Versus here, one group on top and the same group on the bottom, or one group here and one group here that's the same. So because they only have one type of group attached to it, this doesn't have a cis or trans name. This is where the carbon chain ended. So when you're looking at that, look at the molecules, try to determine, does the chain continue through the double bond? If it does it continue on the same side or does it continue on opposite side? That's when you use the cis and the trans names for these alkene molecules in their names. And the cis or trans comes before everything else. So you do the cis or trans, and then the name that tells you how many carbons there are, and then the ENE at the end. And alkenes are actually really important, and the cis-trans nature of alkenes is actually really important for health and food. So if you look at a lot of the different foods that we eat, a lot of our foods contain what are called fatty acids. They have a few other organic groups we haven't talked about, so they also contain this carboxylic acid group. We haven't talked about that yet, so we'll just ignore it for now. But they also contain double bonds sometimes. Sometimes they only contain single bonds, like the one over here. This is a saturated fatty acid. If you look at all the parts down here in yellow, everything on this molecule is single bonds. So ignoring the green, all the yellow components are all single bonded. So that would be a saturated molecule or an alkane. If you compare that, again, ignoring everything up here in green, so if you look at these other 2 molecules here, which are unsaturated fatty acids, you can see one is single bonds, and then there's a double bond in that molecule. And if you were to follow the chain of this double bond, you would start here, you would go to the double bond, and then you would continue on this way, and you form a cis kind of shape where those molecules are on the opposite side, or on the same side of the double bond. They don't cross the double bond. So this would be what's called a cis unsaturated fatty acid. You can compare that to this one over here where the chain starts, it goes here, it goes here, it goes here, it goes through the double bond, and then it goes to the opposite side. And this would be a trans unsaturated fatty acid. So both of these are unsaturated fatty acids because they contain a double bond, but one contains a double bond that's in the trans conformation right here, and one contains a double bond that's in the cis conformation, like the one over here. And because of that, they actually pack together differently. So animal fats have lots of saturated fats in them. These are really, really long fatty acid chains with lots and lots of carbons and hydrogens. And they can either be cis-type fats with a cis double bond, or they can be trans-type fats with a trans-type double bond. But it turns out that the way they pack together, because these are long and bent, the bend that the cis double bond puts in makes the fatty acids have a harder time getting together, and cis fats stay as liquids, which makes them less dense and a little bit healthier than the trans fats, which can pack together really, really tightly and form solids. So if you look at vegetable fats, things like olive oil, that's a liquid compared to something like butter, which is a solid. They both contain fatty acids and oils, but one contains fatty acids and oils with cis bonds, and one contains either saturated or trans unsaturated, and it's a solid. And that can have negative health effects on people as well. So if you look at the way hydrophobic, the way different fatty acid chains react, these are all hydrophobic molecules. They really, really don't like water. They don't have any carbon. They only have carbon and hydrogen. They don't have any polar groups. They're going to avoid water as much as they can. And they do that by all kind of stacking together and forming these chains with all of the little arms that hate water all hanging out together in the center, and then the top of the chain that doesn't mind water as much on top, and then the water can hang out outside. So they're keeping all the water out of the middle by kind of being together that way. So you have this central region right here that really doesn't like water, that's sticking out together, and that's what these fatty acids do. They all combine together, and they make these little vesicles or these little membranes. But when you take fatty acids and you try to pack them together, depending on how much room there is between these little arms where all the saturated and unsaturated carbon chains are, they can be closer together or farther apart. Things like saturated fatty acids like this one here, or saturated that are trans, can actually pack together really well, versus ones that are in the cis position, there's a bend. That double bond with the cis puts a really strong bend, and it actually makes these molecules not be able to pack as close together. So just like if you take a bunch of pencils or a bunch of crayons, they can all pack together really, really tightly together, versus molecules that have bends in them can't as well. So you can see kind of here how the packing of different kind of organic molecules, whether it's a cis or a trans bond, will actually impact how close together we can pack those fatty acids together in the membranes. So here you can see some groups, and because there's this cis bond here going here through the double bond and back, going here through the double bond and back, that puts a bend in the molecule, and it makes it hard for these molecules to get really close together, and there's a good amount of space between those molecules, which means there's a certain amount of flexibility. These molecules on the top can kind of wiggle back and forth pretty well, and this molecule stays as a liquid, which is pretty, and with a pretty fluid behavior, pretty able to move around, and there's some space between those molecules, and it's relatively soft and able to move around. Compared to molecules that are either saturated with all single bonds down here, or in the trans direction with a straight line going down through the double bond and then back in the opposite direction, and then going down through the double bond and in the opposite direction, those pack much closer together. There's a lot less space between these groups up top here than there was in the cis molecule fatty acid. So this trans unsaturated fatty acid and the saturated fatty acids are much more closely packed together than in the cis unsaturated fatty acid. And that means that they are more rigid and they're more solid-like. And in lipids and in membranes, especially membranes that are involved in your veins or in your heart, that can cause there to be a lot of rigidity. And that rigidity can accumulate in your blood vessels and actually result in some health problems. Because of that, the cis unsaturated fatty acids are much more healthier than the saturated fats, and the trans unsaturated fatty acids are extremely unhealthy. And because when we started realizing this, there was some push to make sure that people started not using trans-unsaturated fats. These are what were called the trans fats. And if you look at food labels, at some point they started saying, well, of the fats, how much is saturated fat, how much is trans fat, and then eventually they removed the trans fats completely because the health risks were very high from having these trans-unsaturated fats, which are very rigid and cause the properties of the proteins to be very, very rigid and cause some health defects, versus cis-unsaturated being in a liquid state are much more healthy. So this was part of the rationale for why this ban was put into place in the food. So in addition to all their roles in membranes, alkenes are also involved in polymers and plastics. So a lot of the plastics that we work with are polymers, and polymers are just chains of molecules that have a repeating chemical pattern that is repeated over and over and over again. And a lot of monomers, polymers are made by taking monomers of an alkene, something like ethylene, and reacting them with each other so that you get a long chain of ethylene molecules linked up together. So if you look for an example here, if you take some ethylenes, and you can tell this is ethylene because it has 2 carbons. Carbon means it's an ethyl molecule, and a double bond means it's an ene. So ethylene is just an alkene with 2 carbons attached with a double bond. And if you take 2 ethylene molecules, you can cause them to react with each other in such a way that they form a bond between the 2 carbons that don't have the double bond. So you go from 2 carbon molecules, each with 2 carbons double bonded to each other, to 4 carbons in a line. And you could do that again and again, and you could do this with hundreds of ethylene molecules, and you would produce a chain like this. It goes C, C, and then the next 2 carbons, and the next 2 carbons, and the next 2 carbons, and they're linked here as well. And what you're doing is you're turning an alkene, a collection of alkenes, into a very large alkane. So this is just a really, really, really long alkane that's being produced from lots and lots and lots and lots and lots and lots of alkene molecules. But that's the plastic bottles that we make our soda bottles out of, and our water bottles. So that polyethylene, just if you look in your around your house, you probably have at least 1 or 2 polyethylene bottles. And those are just monomers of ethylene reacted with each other to make this really long plastic molecule that we call polyethylene. And that's the key component to a lot of the plastics that we work with. There's other types of plastic as well. There's also polypropylene, and that's in a lot of the harder containers. So if you look at like the lid of a Tic Tac container, or if you look at a chair that you may be sitting on, that's made of polypropylene. It's again a 3 carbon molecule now. So 1, 2, 3, that would be 3 carbons there. This would be a propylene. Prop is 3 carbons, ene means that there's a double bond, so this is 3 carbons with a double bond. And if you take 2 of those and you react them with each other, you can again react at the site of the double bond and draw a bond between those 2 carbons. So now you have this pattern where it's an up, across, up, across, up, across, and you can see that pattern here. Here's the original monomer, here's the new monomer that was added on, and here's that carbon backbone chain. So it's a sawtooth pattern with another carbon sticking up, and another carbon sticking up, and another carbon sticking up. So we got this new pattern here, and this is a little bit more rigid than the polyethylene molecule we have, and this is why these plastics are a little bit harder and a little bit more sturdy. Polypropylene plastics are a little bit harder and sturdier than some of the polyethylene plastics, and they're used to make a little bit sturdier containers. A lot of medical surgical supplies for plastic are also made of polypropylene. So that's a different type of plastic we can make by just modifying which polymer molecules we start with, which monomer units we have. Do we use an ethylene versus a propylene molecule? They're both double bonded carbons, they're both alkenes, but by switching which alkenes we use, we can create different types of plastics. We can also make another type of plastic like polystyrene. Polystyrene is also an ethylene molecule, but it's got this really big ring attached to it. And again, we're going to attach at the site of the double bond, and now this ring will be sticking off. And you can see here, this is the original backbone chain with these rings sticking off of it. And that creates a different type of plastic. And this is polystyrene made from styrene monomers. Any kind of small yogurt containers or a styrofoam cup is made of polystyrene, but also the dark part of the CD case is either white or black or green or whatever color your CD cases are. The outside is usually polyethylene. The opaque side is usually polystyrene. So these are different types of plastics that can be made by reacting different monomer units. And the monomers are always alkenes because the double bond carbon reacts with another double bond carbon and it puts a bond between the two of them. So rather than having 2 carbons with a double bond, you have 4 carbons with all single bonds between them. So lots of different types of polymers can be made. These are just some other different types of polymers that exist. You have polyethylene. If you go and put fluorines on your polyethylene instead of hydrogens, that creates what's called polytetrafluoroethylene or Teflon. That's what makes all the non-stick pans in your house. You also have things like Kevlar. Kevlar is a polymer as well. Polycarbonate from Nalgene bottles. These are all different types of polymers that all have different types of functionality, but they're all based on these ethylene or alkene type monomers. You can always tell what kind of plastics that you have by actually looking at the bottom of the bottle of the plastic. Somewhere on there, there'll be a little number that tells you actually what the bottle was made of. So whether it was a number 2 or a number 4, that means you have a polyethylene. If you have a number 3, that means you have a PVC, polyvinyl chloride. If you have a 5, polypropylene, 6, polystyrene, 7's the catch-all for everything else. That little number doesn't mean that it's recyclable. It just tells you what type of plastic it is. So this was a way when they started recycling plastics, they wanted to be able to know what kind of plastic things are made of. And it's hard to tell sometimes whether something's made of one plastic or another. So this little stamp is a way of identifying what type of plastic is there. And it looks like the recycling logo because it aids at recycling plants because it helps them sort out the plastic that is recyclable from the plastic that's not. So if you live in a town, it's very hard to recycle polyvinyl chloride. Very hard to melt it down and react it. So this is like at this recycling plant, if there's any PVC in the bins, they go through and they pull out all the ones with 3, and they know that's one that can't be recycled. So it's a way to kind of sort plastics without having to break them out down to their individual molecules. So that's what those little numbers mean. But recycling is a very important process. It's a way of getting more of those molecules back. So when you do this reaction, like the ethylene, the polypropylene, the styrene, those are all molecules that come from oil. So petrochemicals are molecules that come from oil, and we take tons and tons and tons of ethylene, and we use it to make plastic. Lots and lots of worldwide ethylene is used to make plastic, but they don't break down very well. And they don't, if you put them in the landfill, they take forever to break down, and it takes a really long time for them to break down. So rather than putting them in a landfill and using them just once, they're recycled. And that has 2 benefits. One, it minimizes the need for putting more stuff into the ground where it's going to take up space for a while. It also helps out the industry because rather than buying more oil and breaking that down into small molecules, they can break down the old plastic into small molecules, and they can essentially reuse those molecules to make new plastics. So by throwing away something or recycling something that doesn't biodegrade, we're just using it again and again and again, rather than having to use up a limited resource like oil to make more of it. So that's why recycling is important. And recycling is also particularly important because of the amount of stuff that we use. We use a lot of plastic, and a lot of it can be melted down and reused for other stuff. So even like your old water bottles can be recycled to make new furniture, to make new water bottles, or even to make things like carpet or different textiles and cloths. Reusing plastic bags into other plastic, taking plastic food containers and melting them down and making new plastic. And we've been doing this for about 50 years. And because we've been doing it so long, we've gotten really, really good at it. And it's actually very efficient. So it's more efficient to recycle plastic than to make new materials from oil. So it's a more beneficial method to save the environment and to reuse these processes. So rather than being wasteful and getting more oil, we can actually just recycle the plastic that we have since it was going to be thrown away anyway. And because of recycling, it's important to know that we do use lots and lots of plastic, which is why part of the reason why it's really important we recycle. On average, every second in the US, there's about 1,500 plastic bottles that are used and drank and then thrown away. So a lot of plastic bottles are constantly being used. And if we had to keep making new plastic bottles, we would be using lots and lots of material. So even recycling a small amount of these prevents a lot of oil from being used and lets us recycle materials and reuse them again to make a new bottle. Because if we're throwing away 1,000 bottles, that means we're also making 1,000 bottles to replace them. So we need to have lots of plastic. So that would be 2,000 bottles of material. But if we could recycle some of those, maybe only we need 700 bottles. So even if we only recycle a quarter of them, that's still a quarter less plastic that has to be produced to replace the ones that are used up. But you could do a dimensional analysis type problem and actually figure out, how many bottles is this a year? So if every second there's 1,500 bottles being discarded, and then you take the fact that every minute is 60 seconds, so now our seconds cancel with our seconds. And then we go from minutes to year, and it actually turns out there's 525,600 minutes in a year. If you ever see the musical Rent, 525,600 minutes. That's a quick conversion. So minutes cancel with minutes, and that's how many bottles we're going to produce in a whole year. And it's a lot. It's 47 billion bottles a year of plastic bottles are used and discarded. And even if we only recycle 30% of them, that's a pretty big impact, because 30% of those, multiply that 47 billion times 0.28, that's 13 billion bottles a year that are recycled. So it's only a third of the bottles, but that's still a massive amount, because that's 1/3 less bottles that have to be made from new oil. Instead, those bottles can be made from recycled oil. So we don't have to remove as much oil to make the other bottles. So 34,000 or 34 billion go away, but 13 billion. So when we're making the next batch, we only have to make 34 billion from new oil. So just like with the other groups we talked about, there's the double bonded compounds, the alkenes. There's also molecules with triple bonds, which are the alkynes. So alkynes are just hydrocarbons that have one or more triple bonds, and maybe they only have one triple bond, or maybe they have multiple triple bonds. But as long as you have at least one triple bond, you have a alkyne. And when you have a triple bond between two carbons, those two carbons are going to be in a straight line with the two elements on either side of them. So this compound here is a linear compound, opposed to the compounds that we had before, which are more flat. So the alkenes are triangle-shaped compounds. The alkynes are linear compounds, so we have a slightly different shape, and that's much different than the tetrahedral shape of the alkanes. So both the alkenes and the alkynes, when they have this double bond, they become more flatter shaped molecules, and they're straight line, and they're really similar in other ways as the alkenes. So both the alkenes and the alkynes both have double bonded or triple bonded carbon, and they have relatively similar properties chemistry-wise otherwise. So they can participate in all the same reactions, they can do polymerization type reactions, any of the reactions that happen with an alkene, you can do with an alkyne as well. And you can name all these, and you can tell from the names by just looking at the last few letters, whether you have an alkane with all single bonds, an alkene which has a double bond, or an alkyne which has a triple bond. So looking at the last three letters of an element or a molecule will tell you which of those common elements are there. So you can see here this molecule triple bonded is an alkyne, and it has a YNE ending at it. So the YNE ending indicates you have a triple bond, the ENE ending has a double bond, and the ANE has a single bond. And you can remember that it's alphabetical order. So ANE, A comes first, so A is the first. ENE comes second, AE is the second vowel that has a double bond, and Y is the third in that list. So it goes AEY, alphabetical, 1, 2, 3, to help you figure out whether you have a single, double, or triple bond present in your molecule. And as long as you have only single bonds, you're an alkane. But as soon as you have a double bond, it becomes an alkene. As soon as you have a triple bond, it becomes an alkyne. And you can also tell from these, from the first letters, in this case hex, because all these have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. They all have 6 carbons, so they're all hex something, but 6 carbons all with single bonds is hexane. 6 carbons with a triple bond is a hexyne. So you can tell a lot from just looking at the name of the molecule, how many bonds you have, how many carbons you have, and whether or not you have single, double, or triple bonded molecules. So the last bit we haven't really talked about as much is the aromatic compounds. So those are also compounds that contain double bonds, but these are compounds that contain double bonds in a ring. And this is a special molecular structure, sometimes called a benzene ring. You can see here it's a series of alternating single and double bonds. So I'll just highlight the single bonds right here, 3 single bonds, and then 3 double bonds over here, 1, 2, 3. And that's called a hexane, a benzene ring. Again, with this, it's a hex molecule, 6 carbons, but it's 6 carbons with a special geometry, special structure, and those are called aromatic compounds. And as long as you have an aromatic ring, like this one here, this benzene ring, those are called aromatic compounds. So this is an aromatic compound, and then so is this one over here. This is 2 of those rings attached to each other. So these are also aromatic compounds as well. Aromatic compounds contain a benzene ring, this special ring, and then aliphatic compounds do not. So everything else we've talked about today has been an aliphatic compound because it doesn't have these rings, but these ones do. So these are the aromatic compounds, and this is another special type of unsaturated molecule that carbon can form. And just to kind of end today, we'll show you that you don't have to have just 1 ring or 2 ring. You can have a lot of rings. So you can have some of these compounds, these polycyclic aromatics that have lots and lots of rings on them. So you can get some aromatic compounds with multiple rings on them, all fused together. And these are all still aromatic compounds because they still have lots and lots of double bonds in a ring as a molecule. So that's it for all of the different hydrocarbons containing just hydrogen and carbon, sometimes having a double or a triple bond as well. So next time we'll talk about some of the other organic molecules that include oxygen and nitrogen bonded to those carbons as well. But have a good weekend, and we'll see you guys next week.